It says that Tuesdays and Thursdays are recitations. Forget the registrar schedule, okay? We will meet every day that Dr. Belmar or I are present, and there will be 24 live lectures, and then sometime around November, beginning of November, you'll all get to do a presentation, and I'll talk about that more. And that's the only requirement other than coming to class and looking at the handouts. And part of that, well, there's several reasons for that. The course has evolved over the years, and a few years ago, Professor Hsu, when he's chairman of the graduate committee, asked me to expand it beyond what I've been doing for years, which was a welding course. I kind of got my tenure in welding in joining, and then I kind of switched it over to a manufacturing course, and I taught some selection of materials and some other things, but they asked me to broaden it, particularly because there's not that many faculty left that deal with metals and structural materials, okay? And so there's historically about 25 years ago I started teaching with a video, okay? And we did this because General Motors wanted to take my welding course as part of their master's student or master's program they ran for their students. Well, in any case, I learned after about a year that videotaping the lecture is not a bad thing, because if you miss class, you can watch the movie, okay? And in fact, I could lecture more topics and then the students could watch them at other times. I used to have students in the LGO program go off to their 7-month internship and take my course, and some of them would say they would watch the lectures while they were fixing dinner or other things. But part of all of this is I was an MIT undergraduate. I've been here since I came here 45 years ago, and I've been on the faculty. This is my 38th year on the faculty. And about 25 years ago, I came to this conclusion that the way we teach at MIT is all wrong, okay? You're all very smart, and you've all gotten here because you know how to take quizzes, okay? And basically, the students, particularly the undergraduates more than the graduate students, and the earlier undergraduates, I used to teach sophomore thermo, but they're worried about their grades, and they're worried about the quiz, and they focus on that. And they're not focusing on just trying to learn. So 30 years ago when I started teaching the welding course, I decided, well, this is sort of silly. No one has to take my welding course. We'll just do it, and we'll enjoy doing it and learn. When I was a student, I hated problem sets. I hated 3-hour finals, and I remember how much I hated those things, and I won't make you endure those, okay? I do have to have something to grade you, okay? The Institute says I must grade you each individually, not as a group. And so you have to do something. And so more recently, what I've been asking the students to do is a presentation on whatever interests you. Now, hopefully, you can fit it into somewhere. This course is supposed to be about structural materials and material selection or whatever. Maybe you're interested in bicycles, and I've had students do, materials of construction of bicycles, okay? There's lots of different things you can make a bicycle out of, from a $100 bicycle to a $10,000 bicycle, right? And so I've had people do doorknobs. One person was interested in decorative doorknobs, okay, through the ages, okay? So you will have to do a 15-minute presentation, okay? And we'll actually should be about a 12-minute presentation, and we'll do 3 a day, and with 10 of you, we'll finish that up in a week. If all goes well, you'll be finished well before Thanksgiving with this course, okay? All you have to do is come to class, and I find it's easier just do it every day, unless Dr. Belmar, who will be lecturing some of it, and I are both out of town, then you can have the day off. We do have a need for the future for someone to videotape. Steve is doing it today, but he has classes Monday, Wednesdays, and Fridays at 9 and another thing. So who would like to earn $1,000 and come to class? Okay, will the two of you get together with Steve and you can share it? I'd love to have 2 people sharing it. It might give you a little bit more than 1,000 to do that. There's also loading it onto the website, okay? But Steve can show you how to do it. And then if one of you the reason I like to have 2 people is if one person gets sick, the other one can coordinate, okay? But that's how we get the videos, right? And so Steve's got the equipment, and if you have time after class, if you can talk to him, okay? It works out to about $50 an hour, so it's a fair price, okay? I think. If it's not, let me know. And so essentially, that's all you have to do with that. So thank you for that. I did write an article about, how long ago is this? 2004, in the MIT faculty newsletter about leadership management and education at MIT, and essentially what I think makes an MIT education different than most other schools. For example, there's only 2 schools I know of that only admit 1 class of students, and those are Caltech and MIT. And what class of students do we admit? Scholars, okay? If you go to Harvard, they admit 3 classes of students. Anybody know what the 3 classes are? Scholars, okay? I'll give you a hint. What's the other one? Another one. Athletes, okay? And the third is, they call legacy students. That means sons and daughters of wealthy alumni, okay? And so, as a result, and Princeton and Stanford, Harvard will admit they admit 3 classes of students. This is not a secret, okay? They freely admit that they admit, athletes who ordinarily wouldn't be qualified as scholars, and legacy students who were too dumb to go anywhere else, okay? But their parents gave millions of dollars, or their grandparents gave millions of dollars to Harvard. Anyway, Princeton, Yale, Stanford, they all admit 3 classes of students. Caltech and MIT, so far as I know, admit only 1 class of students, and that's scholars, and that allows us to do a freshman year that is completely filled, no electives, and everybody starts out with calculus, physics, chemistry, biology, and humanities, right? No choice. Isn't it a wonderful system? But essentially it allows us to homogenize academically your background in that first year, and then you get to accelerate in succeeding years. So the freshman year is not sort of wasted on all this other stuff, okay? So it increases the pace and pressure of MIT, but there are 5 things in here that I think makes MIT unique, and so you can read about what I think is unique about MIT after over 40 years of being around here as a student and a faculty member. You have to take 3 modules, but only 2 of them are going to be live this term. I'll be lecturing on material selection at sort of a high level, non-destructive evaluation, and if we have time, I'm supposed to do some welding metallurgy. There's some people in course 2N, the Navy program, that I teach during the summer, and if you take some of these other modules, you may see those were taped during the summer, and I tend to give lots of naval examples to these Navy students. Dr. Belmar will be talking about material selection and structural and environmental effects on materials. His material selection, well, my material selection is a much broader overview than his. His is specifically what types of materials do you choose for structural materials. You'll see I talk about all kinds of things. He will also talk about casting, forging, let's see, he gave me a list of casting, forming, which I call deformation processing, joining, which I have 2 modules on, and coatings and surface treatments, which I don't really cover. But he's going to be spending 1 lecture each on those, and then he's going to spend 8 lectures on environmental and mechanical behavior, which is how do you design with structural materials. So I'm going to do a broader view of some things, he's going to do a broader view of other things, and others will get more specific. You don't have to take his live or mine live. In fact, you don't have to take any of them live. You could pick, these are the video things that are online. There's solid state. I've been teaching a version of these first 2 for about 30 years now. And this is welding, soldering, brazing, cold welding, diffusion bonding, adhesive bonding. Fusion welding is flames, arcs, lasers, electron beams. I've done one time, since Professor Hsu asked me, on casting, another time on deformation processing, which is forging, rolling, drawing. I've done a couple of times on codes and standards, and Dr. Belmar has done structural life assessment and selection and processing of structural materials. So in any case, we will give you the schedule as we know it, which is not usually more than about a week and a half ahead, other than you come to class every day if you want to take both modules that are live. And I'll be lecturing 2 days, he'll lecture 2 days, I'll do 2 days, and he'll do 2 days out of the first 8 days. So by the end of next week, you're 1/3 done with 2 of your modules, okay? You have to pick one of the other modules. And if you want, you can come sit down with me. If you know, anybody taking this course for a particular reason, it's not on required lists. I guess it's a restricted elective now or something, right? Anybody have a particular reason? You're in nuclear, you want to learn something about materials, right?
My research is nickel superalloys.
Okay, so nickel-based superalloys. So if I remember that, then I'll try to weave in some nickel-based superalloys. Okay? Anybody else have anything? No one is going to go work for Boeing or something and I need to talk about aircraft materials, or anyone going to build houses for a living? I had one student years ago whose father ran a boatyard down here in just south of Boston. That's what he's been doing for the last 30 years. Is got his bachelor's degree, straight A student at MIT, went off and he's been building fancy boats for rich people. Anyway, so you'll have to pick one of these others, and you'll have to watch those by video at your time. They're on the web. The website needs to be cleaned up in the next week. If you go look at it right now, you won't see things quite this coherent on the introductory page. Yes?
Can you just clarify, so there's a live lecture every single day you choose to go to for, and then?
Well, you need to take 3 modules. So there are 2 modules that will be live, and Dr. Belmar will do one and I will do one. You can choose those 2 live as 2 of your 3 if you want. Otherwise, you could choose one of those, his or mine, and you should go the days, if you're only doing one of the live modules, you should only go on the days that, you know, that person's lecturing, okay? We're kind of alternating so we have time so we can travel and do other things.
So
and
when you say like 4, 5, 6, those are like literally today, tomorrow, the day after?
Right, yeah, these are the dates in September. Today's September 4th. E means I'll be lecturing today and tomorrow. He'll be doing Friday and Monday, okay? Right. So it's always in this classroom. If we don't miss any days, I think we finish up the 24 hours of lecture in early October, like before Columbus Day. But then you've got to watch another 12 lectures whenever you want before grades in December. If you're smart, you'll pick one of these other things sometime in the next few weeks and you'll watch those while you fix dinner or, you know, whatever, right? They are on the website. Now, so far as all that goes, over the years, my lectures are sort of Tom Eager in stories, okay? I have a fair amount of experience and a lot of different problems that the world has faced, because I go back to the beginning of time and things like that. But in any case, that's why it'd be hard to grade you on these things, okay? You just have to kind of, hopefully you'll learn something. I've had students come back and tell me, you know, 2 or 3 years after they graduated, they got more out of my course that's useful than any other course they had at MIT. I mean, I don't remember how to integrate sine x over x. I took that, okay? But I don't remember how to do it. And I don't do that type of thing every day. I learned differential equations, okay? I passed it. In fact, I thought they were sort of simple, just sort of cookbook algebra as far as I remember. But anyway, that's not what I do every day as an engineer, okay? And so I would rather talk to you about real engineering problems and all the complexities of those things. I also have a difference in philosophy of a lot of faculty, and this is not just MIT, it's everywhere, Many faculty want to impress you with how much they know, and they're going to impart this to you if you pay a big tuition, right? Okay. I would much rather try to convince you that you already know most things you need to know. You just need to learn to organize it. Organize your thoughts. Okay? Like I have in one of the arc lectures in fusion weldings, I talk about arc physics. And there are arcs in this room. I'm looking up at them, right? Fluorescent lights are arcs. They're a little bit different types of arcs than a welding arc. But in fact, they're still got the same physics of an electric arc. It's just, it's a 2-temperature plasma as opposed to a welding plasma, which is 1 temperature. And that all has to do with the pressure of the arc. The physicists call a welding arc a high pressure arc. Anything above a half an atmosphere is a high pressure arc. A fluorescent light is significantly less. It's even less than 1/10 of an atmosphere. You ever broke a fluorescent light and it goes pop? It's because it implodes. It doesn't explode, it implodes because there's a vacuum inside the glass. And because of that, you have a long mean free path between the molecules. And it turns out the electrons have a temperature in the fluorescent light of about 100,000 degrees. But the ions have a temperature of about 200 degrees. It's a 2-temperature plasma because the electrons get accelerated in this partial vacuum. Whereas in a welding arc, it's all local thermodynamic equilibrium. The ions and the electrons all have the same temperatures. Don't go putting your finger in a welding arc, you'll get burned. But you can hold on to a fluorescent light and you won't, because the ions carry the heat and the electrons don't have any heat capacity. Okay? So these are some of the types of things you learned about heat capacity, but no one ever taught you how to use those ideas. Okay? Hopefully that didn't confuse my little thing didn't confuse too many of you about the difference between a fluorescent light arc and a welding arc, and why one of them's hot and one of them's cold. One of them gives off light and the other one gives off light, because the electrons are the things that give off the light, right? And if you start thinking about LEDs, well, that little LED, those electrons have lots of electron volts. And so they radiate and give off light, even though an LED is even cooler than a fluorescent light and uses less energy, right? It all sort of fits together. And I didn't tell you anything you didn't sort of already know, but no one ever taught you how to put it together. Okay? They taught you how to take a quiz. Okay? Well, bull on that. Okay? You don't have to take a quiz. You can just sit here and try to figure out what I'm talking about. And that's another problem with the way I teach, is I would much rather talk about some question you have and see if I can put it together. That makes the challenge for me. I've been lecturing this stuff for 25 years. I've heard it before. And just come in and lecture about what I've talked about 10 times before is not as interesting to me. I'll have some things, and I have lots of touchy-feelies and try to put things together and tell you a story, but I'd rather have you ask questions and stop me. And some people say, well, he's disorganized in his lecture. I'm not completely disorganized, but I don't, and the reason I use an Elmo, I'm not going to put it on a computer. I don't know what my next slide's going to be, depending on your question or what I'm thinking of. Okay? I do have an outline. It's just I don't follow it. Okay. Okay, so let's see if there's anything. Any questions on any of this? So I told you about, grading. Don't worry about grades. I've been doing this for 25 years. I've only given 2 grades. Okay? Top and bottom. If you don't come to class, I've never seen you, don't even know who you are, the registrar makes me give that person an F. Otherwise, and if you're a senior, I would not choose this as your pass-fail course. Okay? You got another choice, right? So I'll leave it to you that way, because we're not doing this for grades. You're far enough along in your career that you shouldn't be worrying about grades. The philosophy is, let's try to learn and don't toil. Okay? Most of MIT education is how to make you toil and learn to work hard. And that's a great experience, and if you read my faculty newsletter, that's one of the things you learn at MIT. It's one of the things that makes MIT great. You learn to work hard. But at this point, let's just take a breather and try to learn, okay? Rather than just work hard, okay? The problem I have with the courses is a lot of times they just get into working hard. I will also try to tell you some great secrets of MIT. Has anyone ever been to a class where the professor spent the whole time doing a proof, a derivation? Seen some nods. Have you ever thought about why the professor did that?
But you know how to go from first principles to it.
That's a good idea, okay? It's not the reason, but it's a good idea. And they would tell you that's why they're teaching that way. I'll tell you a secret. My first year on the faculty, I had a trip and I came back the next morning and I had to lecture on deformation processing. And I hadn't prepared the lecture. And so I only had about an hour and a half to figure out what I was going to talk about that day. And I looked in the book, this is Professor Backhoff's book, and there was a derivation. I thought, great, I'll just go in and fill the time with the derivation. And all of a sudden a light went off and I thought, oh, that's why professors do derivation. They didn't have time to prepare a lecture. And I did that. I went in and I did the derivation. And I went back to my office and I swore to myself I would never do another derivation in class. So I used to teach thermo without doing derivations. What would I do? If the derivation was in the book, I assumed that MIT students are smart enough to follow the algebra in the book. Okay? If the derivation was in the book, I would write it out, copy it, give the students a copy of it. I'd say, here's the copy. Let's talk about what it means and how you use the result. Okay? And yeah, you could learn the same thing that you just said, how to go from first principles or this equation to that equation, but you can do that on your own. You don't need some PhD professor up here charging you, what's tuition now, $28,000 or something, whatever the tuition is. When I started it was $22.50, okay? It just gone up from $1,900 and the students were really upset. But in any case, you don't need someone coming up and walking you through the algebra. That is a total waste of time. You fall asleep, I fall asleep. The professor always makes a mistake, right? Okay? What's the point? Okay? So now you can see where I kind of diverge from the MIT philosophy of education. But there are other things that professors do that if you actually stop and say, why do they do this? It's because they procrastinate, so they want you to procrastinate. I mean, one time when I was a sophomore, I had a term papers due in a humanities class. So Columbus Day holiday, I spent that Monday in the basement of Walker, looking through all these books, doing all my research. 2 or 3 weeks later, I had it all typed up. I gave it to the professor in October before mid-December. And he gave it back to me. He says, I don't read drafts. I gave it back to him. He said, it's not a draft. Okay? He says, he gives it back to me. He says, it can't be. It's not the end of the term. I said, it is the final copy, and I know it's not the end of the term. I get things done early. Okay? He couldn't fathom it. He was used to doing everything in his life at the last minute. Okay? So why do I want you to be done with this course in early November? So you only have, how many courses are you taking? 2? Okay, how many courses are you taking? 4? You only have 3 courses from November on, right? What a deal! Because the professors are all trying to cram it. Why do we have rules that you can't give all this stuff if you have a 3-hour final at the end of the term? Because the professors are all used to procrastinating and they're trying to cram it down your throat in the last 2 weeks, right? Okay, so that's why we have some of these rules. These are some of the reasons why I don't believe in the educational philosophy. Okay? So, anybody have any questions on that? Okay, so let's start talking about other things. There's nothing wrong with having that introduction on the video. You will see, and I apologize if you watch some of the videos, you might hear some of the same stories. I don't have an infinite amount of stories, and I don't keep track of what I talked about one year or the other. This came out of the Christian Science Monitor back in the 1980s at the Graduate School of Business. Now I know you all want to make money, but today we're going to discuss making things, actual things. And things. I don't want to make things. I want to make money. Listen, let's sue the business school. We can make some money that way. And that's kind of the philosophy of a lot of people, okay? But let's talk a little bit about what in material selection, if I'm a materials engineer and I want to select some material, it turns out I am no longer capable of just doing engineering the way people used to do it even 50 years ago. I have to worry about what the economists call externalities. Has anybody taken an economics course and ever learned what an externality is? You're shaking your head like you know.
Yeah, so an example would be like pollution. So you may make a decision to produce a product because you know you're making a product, but then you're polluting the environment and everyone else has to deal with that. So externalities.
Right, so there's social implications to what we do and how we do it, okay? And Professor Sadoway has built up a great big research program on batteries for energy storage because it's going, he used to tell me 15 years ago, chemical metallurgy is we polluted the environment, now we're gonna clean it up. And to a certain extent, he was absolutely right. Who else deals with 1 billion tons of material? And if you gotta clean up 1 billion tons of material, you ought to figure out how to do it as part of your original process. Okay, and so that's kind of led him down to some of these things. The example I like to give of the externality of pollution, the rules have changed over the years. I had an explosion in a oil refinery in Oil City, Pennsylvania. Anybody ever been to Oil City? Okay, it's up in the northwest corner. It's just down the river from Titusville. Anybody know what Titusville is famous for? It's where Edwin Drake discovered oil in like 1856, and that was the beginning of the drilling for oil. Otherwise, they used to just find oil bubbling up out of the ground somewhere. Anybody know where they used to find oil bubbling up out of the ground?
Texas?
Well, it did occur in Texas. Yeah, but I used to always wonder why the Strategic Naval Petroleum Reserve, even back in 1900, was in Prudhoe Bay, Alaska. And I thought, well, who was drilling for oil in Prudhoe Bay, Alaska? And the answer, in 1900, the answer is nobody. It was just bubbling up out of the ground. Okay, and so someone knew, must be something underneath the ground if it's just bubbling up, right? Now, a lot of the year it didn't bubble up in Prudhoe Bay, but they knew that there was oil in the ground. The whole tar sands of Alaska, how did that get there? Well, it bubbled up out of the grounds and all the volatiles went away, and now it's tar, because all the lower chemical species are gone, right? I mean, you already knew some of those things. You just never thought about why there are tar sands in Alaska. It just bubbled up out of the ground and the volatiles evaporated, and now we're full of tar, and now we're just trying to reconvert it back and add some lighter hydrocarbons so we can now make it flow again, okay? But it started out as liquid oil, okay? Anyway, so, but the story, finish my story on Oil City. So I go out to Oil City, and this refinery, and now I went there in the late 90s, this refinery had been built around 1900, run by Pennzoil at the time, a major oil company, and I go there and they got riveted steel tanks from the 1920s, and it wasn't anywhere near the size or scope of some big refinery in Houston or in California that I've been to or something. I thought, how could Pennzoil run this inefficient, small-scale little refinery in Oil City? And I was there for 2 days. The second day, it hit me. They could run it because they couldn't afford to shut it down. If they shut it down, the EPA was going to declare it a hazardous waste site, and Pennzoil was going to have to pay hundreds of millions of dollars to clean it up. If you dug down 2 feet in the rock gravel in the tank farm where all these tanks were, you'd strike oil. They've been spilling oil there for 195 years. And so the whole place was a hazardous waste site, but as long as you're in business, it's not an EPA site. As soon as you go out of business, it's an EPA site. And now the company has to pay the government to clean it up. So Pennzoil was trying to clean it up themselves rather than let the government go in with their blank check and their great efficiency that the government is known for in doing things like this, right? So, but let me tell you the story that really struck me. How do you think they got the oil from Titusville upriver down to Oil City 100 years ago?
Road in the river.
Floated it right on top of the river, right? And they just skimmed it off at the other end. And I bet there weren't a lot of fish in that river in that section, right? But nowadays, you see a little sheen of oil on the Charles River, and they're going to go out there, and the EPA and the environmental police are going to sue somebody for a couple $1 million for just a little sheen of oil out there. Okay. In Canada, they have $100,000 geese. You know, I always say, hey, come over here to Belmont where I live, and right next to the high school, we could make millions of dollars. They got lots of Canadian geese. And you walk down the sidewalks and you're stepping all over it. But they have these tar sand ponds up in Fort McMurray, where they have the tar sands, that if a bird flies and lands in the pond, they'll get coated with oil, and they will no longer have their water repellency, and they will die. And so to encourage the tar sands people who are making lots of money not to kill these poor Canadian geese, which the world I guess we don't have enough Canadian geese or whatever, they fine them $100,000 a bird for every bird that lands in the pond. And a few years before, 3 birds had landed in the pond, and they fined them $300,000 for killing 3 Canadian geese. And I thought, well, hey, I'll sell you some. I'll give you two for $50,000. Okay, but now you go there, and as you're driving by, you hear boom, boom. They have these little rafts out there in the pond that are propane cannons, and they're basically just shooting off noise to scare the birds away. Okay, because it's cheaper than paying $100,000 per Canadian goose that dies, right? These are externalities. What are some other externalities? Anybody? Yeah, go ahead. Pardon me?
Smoking.
Smoking is an externality. Now, I'm not sure that immediately I can think about how to tie that into material science. However, actually I can. When I was department head, there was a guy, got a moth in here. Guy Nick Grant was a faculty member in the department, and he was trying to get some research money. He was well into his 80s, and he was going to get some money from one of the tobacco companies because he made powders, metal powders all his life, and they wanted him to make some powders of different composition, and they wanted to absorb the smoke, okay? So the cigarettes might have metal powders as activated rather than activated charcoal. I don't know. But they were going to give them hundreds of thousands of dollars. I mean, here we're trying to raise research money from the government. These guys were just floating in money, and they wanted to have them. Anyway, so yeah, even in smoking, there's some material science somewhere, okay? Anybody got any other examples? How many of you are have heard or worked on rare earth materials, or read the papers about what happened in rare earth materials about 4 or 5 years ago?
Then when China decided to stop exporting so much?
Yeah. It's not that China has all the reserves of rare earth materials, but they have tremendous mineral reserves of rare earths. And so as they started improving their economy, they started manufacturing lots of rare earth materials and cut the price so that all the other mining companies just shut down. They couldn't compete with the Chinese labor market for rare earth materials. And then there was a little political, which is an externality, fight with Japan over, I guess, some of the islands in between or something. And so the Chinese decided to be punitive and cut off rare earths to Sumitomo Metals. That's the only place in the world that you can buy rare earths right now is China. They created a monopoly not because they're the only ones that have rare earth minerals, but they had reduced the price because of the cheap labor rates and their very good resources on rare earths, and no one else wanted to compete with them. And then they used that political clout to essentially threaten the Japanese with a huge industry. What are rare earths used for? Electronics, specifically neodymium iron magnets, right? Okay, in another lecture you'll learn about fiberware pots, and how there's different magnetism here versus up here, and anyway, that's another topic. Okay, but there was my example of a neodymium iron magnet. There's also samarium cobalt, and so rare earths are important. And why are these permanent magnets important? You're all too young to know. When I was an undergraduate, when I was the age of some of you, we got a field trip to General Electric's research labs, and they were making samarium cobalt magnets. This was before neodymium iron boron had ever been invented. And General Electric had a huge project to make samarium cobalt. The problem with samarium cobalt is about half as strong as neodymium iron boron, but it was much stronger than the old Alnico magnets, which were around in the 1930s. And I'm looking for an overhead here, which I just found. I haven't even told you about Norm Augustine yet, but anyway. So here's a plot from years ago of the BH product. What's the BH product for all you electronic materials people? B is the magnetic field, induced magnetic field. H is the applied magnetic field. And the BH product is, how strong is this magnet? How many pounds of force will it, hold or whatever? In megagauss Oersteds, Gauss is B and Oersteds is H, the units. And this is time versus the BH product. And so it's sort of the magnetic field squared, right? One's induced magnetic field, one's applied magnetic field. The two are related by the magnetic permeability. Maybe you learned that once, but you forgot it, but you really knew it, okay? And so it's basically B squared. And steels back in before the 1920s, Alnico magnets in the 1930s, rare earth cobalt. This is samarium cobalt in the 1960s. It was the early 70s. I went to, here's samarium, cobalt, iron, nickel, copper. And that's about the time that I went to General Electric, and this stuff had a BH product of over 30 compared to the old aluminum nickel cobalt alloys, which you had on your little etch-a-sketch, not etch-a-sketch, but remember the iron filings, and you could put the beard on the man and mustache and stuff. That's the Alnico magnets. They're not very strong. And then in about 1980, General Motors Research Lab discovered neodymium iron boron, which is that little thing. And now they're all over the place. So somewhere around 1980, when the Sony Walkman first came out, ever heard of the Sony Walkman? Okay, it was the first little kind of portable music player. Had a battery life of about 3 hours. Why? Because you didn't have these big BH product magnets. And they wasted lots of energy generating the magnetic field to run the video or the tape. The motor that's running that tape was consuming all the electrical energy and creating an electromagnetic field. Yeah, they had a magnet or they had a core, but they're just generating heat because they didn't have good strong magnet. If you have a strong permanent magnet, you can just have a little field and just add a little field to a big field and get very powerful motors that are very small. When I was a kid, and I would rebuild a starter motor for a car, the thing weighed about 30 pounds and it was a great big thing like that. Anybody seen a starter motor on a car today? Size of your fist. Probably twice as powerful as the starter motor I was working on and rebuilding back when I was a graduate student, 40 years ago. Why? Because neodymium iron boron magnets. There's something like 15 pounds of neodymium iron boron magnets on every automobile in the world today. I got power windows, I got power seats, I got, every one of them's got, every one of those dozens and dozens of motors has got neodymium iron boron. And here the Chinese were going to take that away from me. Well, you can't take it away. How much would it cost to redesign all the starter motors on all the cars in the world? Everybody had to start paying these horrendous prices. And then all of a sudden, the government's talking about, well, what are we going to do? Are we going to retaliate? These are the externalities, right? Are we going to open up mines? They've been talking about opening up rare earth mines in California. We have resources for rare earths. We just, but if the price goes up, we can afford to open a mine in the United States. It was only when the price was down low that we couldn't afford to keep it open. So we closed it, but we could reopen it. It just takes about a 5 or 10 year lead time. And $1 billion. Okay, but $1 billion is nothing compared to that externality of the value that the Chinese all of a sudden, they can get a little blip in prices, but they can't get a long-term price increase because other people will come in to take over the market. So whatever you know about materials, there's a short-term economics and there's a long-term economics, and they're not necessarily the same. And there's lots of opportunities to come along because of these externalities. So that's what Norm Augustine's talking about here. Anybody know who Norm Augustine is? Was? What his history is? So Norm Augustine is actually one of the non-MIT members of the MIT Corporation. He was an engineer. He became chairman of Lockheed Martin Corporation. He became president of the National Academy of Engineering. He is a very articulate spokesman for engineering. And he's a very bright, very practical man, okay? I mean, he would do plots for the Defense Department showing the increased costs of aircraft, fighter aircraft over time. And he predicted that in 2020, the entire Air Force budget would be able to, this is in about 1980, that about 40 years later, the entire U.S. Air Force budget would be able to purchase one aircraft at the current increase in cost of aircraft. Okay, well, it's not quite true, but that's what the trend line was showing. If you plot everything on a log plot, everything intersects eventually. Anyway, and then the entire Defense Department budget would only be able, you put Army, Navy, and Air Force together, they could buy one aircraft in 2045. And he was trying to argue that we need to lower the cost of production of aircraft, which they have done, and so nothing's constant. But anyway, Augustine's he coined the term socioengineering. This was printed in the National Academy's magazine. And he talks about the externalities. Now, the externalities can be economic, they can be environmental, they can be political, they can be social. Okay? Anybody think of well, you did think of social, kind of the environmental stuff is sort of social. But that's really like when I said environmental. The social I wrote down were, anybody heard of blood diamonds? Coming from Angola, got a civil war. The problem is you can't always tell whether those diamonds came from Angola, but you can if you're a really good material scientist. You know how to do it? You look for the impurity content in the diamond. You analyze the impurities. And certain diamonds, you can fingerprint what geological region of the world they came from. Before that, about the time you were born, most of you, there was Rhodesian chrome. Anybody heard of Rhodesian chrome and know anybody heard of Rhodesia? Okay. Well, Rhodesia was this East African nation just north of South Africa, and they have the world's best chrome ore. It's so good, you can't reproduce it, okay? And it's the most economical, but they were having a civil war in Rhodesia. And I guess some of the people were murdering other people. And so the rest of the world was trying to pressure them, just like we're trying to pressure Syria right now because of their civil war and things. And so they put an embargo on Rhodesian chrome. And it wasn't as if I mean, it's a lot easier to detect Rhodesian chrome than it is blood diamonds, okay? Blood diamonds, you got to go in with some pretty sophisticated instrument. Rhodesian chrome, you can sort of look at it, okay? I mean, anybody ever heard of the Masabi Range? Okay? Back in the 1920s and 30s and 40s, the United States had the best iron ore in the world in northern Minnesota. It was called the Masabi Range. It ran out in the 1960s. But you could just break up that rock and feed it straight into the blast furnace. You didn't have to do any secondary processing at all. That was the best iron ore in the world. It goes straight into the blast furnace. Okay? Made the United States super strong in steel. You know what made the United States super strong in steel in 1945? The United States controlled 75% of the world's steel production in 1945. Anybody can think of why? It was an externality. It had nothing to do with the Masabi Range or great management or anything else. We had bombed out everyone else's steel capacity. Of course we were the only ones that had any steel mills left. We bombed Germany, we bombed Japan. You know, Germany bombed Russia. You know, I mean, hey, we were king of the hill in 1945. When I went to work for Bethlehem Steel in 1974, the managers who had been hired 30 years later were now top managers at Bethlehem Steel, and we controlled 25% of the world's steel capacity. And they still thought they controlled 75%. That was their mindset. When they had been hired in, they controlled the world steel. In 1962, President Kennedy decided that U.S. Steel decided they wanted to raise steel prices. Well, in 1962, before we had the Arab oil embargo in 1972 and stuff, the price of steel was what the world's commodities were based on. And so U.S. Steel raising the price of steel was going to create worldwide inflation, just like oil does now. Well, it turns out President Kennedy had a big standoff in 1962 with U.S. Steel and forced them to roll back their prices to the prices they had been. Okay? He embarrassed them in public. This is an externality, has to do with the metals business. Some people, a lot of the old guys in the steel industry said that was the beginning of the end of the U.S. steel industry. That's not true. It was when they hired those idiots in 1945. That was the beginning of the end. Those idiots, 30 years later, still thought they controlled 75% of the world steel industry. They only controlled 25%. And guess how much they control today? 10%. Okay? I remember the week I left Bethlehem Steel. Well, I worked for Bethlehem Steel in the research labs, which was the beautiful research labs. $600 million facility built in the 1960s. It would be like a $2 or $3 billion facility today. Sits on South Mountain, just north of Lehigh University in Bethlehem, Pennsylvania. It was just a Taj Mahal of steel research. Vice president was a graduate of this department. Don Blickweed used to be on the visiting committee. In Bethlehem, it looked at innovative things like nuclear steel making here in the You could build a nuclear plant and you use all that electricity from the 1960s and you could make more steel than anybody could ever use. The energy coming out of a nuclear plant is, it'd be like the equivalent of 3 steel plants, okay? But the idea was, at that point, nuclear energy was going to be free, too cheap to meter. Back in the 1960s, they didn't know about the environmental concerns. Anyway, actually they knew about them, they just didn't think they were important. Anyway, so these are externalities. And so if we're going to talk about material selection, you need to think about externalities. And so you can read what Norm Augustine said about this stuff. He's also a very good writer, okay? He writes in ways that help people understand simple things. And if I knew how to teach it, I would try to do that for you too, okay? I don't know exactly how to teach it, but I'm going to hand out a paper which, out of my several hundred publications, is the most referenced paper I've ever written. It took me less time to write this paper than any other paper I've ever written. It took about 3 hours. 2 weeks after the World Trade Center collapse, the editor of a metallurgical journal, the Journal of Metals, actually he called Joel Clark first, Professor Clark, and said, would you write an article on the World Trade Center collapse? And he says, well, why don't you call Tom Eager? So he called me, and I was so sick of hearing people tell me in the newspapers about the fire was so hot that it melted steel. Anyone who's ever been to a fire scene knows that you don't melt steel in a fire. Anybody who ever heard about Sir Humphrey Davy, Bessemer, okay, Sir Henry Bessemer, who taught us how to melt steel in 1856, which brought in the Iron Age, okay, knows that you don't melt steel in a fire. But all the newspapers were reporting, well, the jet fuel was so intense in the fire. Bull, okay? You can look at the photos and you know it wasn't that hot. Anyone who's ever been to a steel mill? Any of you ever been to a steel mill? And you've seen molten steel or, okay, what's the color? Is it red hot? It's yellow or white, right? 2,500 degrees Fahrenheit, 1,600 degrees centigrade is yellow white hot. You didn't see yellow white on the World Trade Center building. You saw yellow, okay? It was, you know, and that's just the Planck radiation constant, okay? Planck's law, okay? And the color that you get from a solid material, and it's actually the sodium or the soot particles that are radiating yellow at you, or red if it's 900 degrees. You actually can look at colors and see the temperature. They call it color pyrometry, measuring temperature with color. And so it's ridiculous. So I ended up writing an article, and I wrote it the person I had in mind when I was writing it was a high school science senior. Okay? I wanted to write it simple enough that someone had a little bit of high school science, could understand it, but I wanted to talk about fundamental principles. And for about 10 years, from 2001 to about 2011, it was the most referenced article on the World Trade Center. If you Google WTC collapse, it was the #1 hit for about 10 years. Since then, it's like now down to like 3 or 4, okay? But I would go to Washington, people would say, oh, you're an expert on the World Trade Center. Yeah, I spent 3 hours learning about it. Oh, duh. You know, and I'm an expert. But actually I was compared to all those other people. But nonetheless, the standards for scholarship are not very high out there. Okay, they might be higher here at MIT, but out there in the real world, the standards for scholarship are not very high. It turns out I became the brunt of the conspiracy theorist. Originally, well, I remember the article came out in December of 2011. I wrote it in beginning of October, but it didn't come out for a couple of months. And originally I started receiving these emails, and they were from people who said, oh, the whole thing was a conspiracy between Israel and the United States to get everyone upset with the Palestinians or the Arabs. And I thought, huh? How did they get that out of my, anyway, they were taking issue with it, okay? And so when I taught my thermo course, they would have calculations. I got a book that one of the graduate students in this department gave me because he was a conspiracy theorist. And there was an article in there that calculated the maximum temperature of the fire was 500 degrees Fahrenheit. And that's not even good enough to cook a good pizza, right? I knew from the yellow it was actually around 900, and you'll see the reasons I give you thermodynamically in there, in that paper if you want to read it. But people will throw out all kinds of things and they never put numbers on it. And so one of the things you need to learn is how to put numbers on things, okay? And challenge me when I say something and you say, well, how to put a number on that? And let's see if I can do it, okay? And when you do your presentations, try to be quantitative, because Lord Kelvin said, if you can't express your ideas in numbers, you haven't reached the stage of science, no matter what the matter may be. So I would like you to learn a couple of things from this course. One is to realize that you already knew the answer. Okay, you already took all these courses at MIT, and they taught you enough that if you put it together the right way, you can figure it out for yourself. You don't need a professor to do it. You can figure it out for yourself. And the other thing is, I'd like you to learn to be quantitative, to put numbers on things. And if you do that, I promise you that you will be considered one of the greatest scientists and engineers when you get out there among the rest of the people who can't even count to 5 without tripping over themselves, okay? You went to MIT, you can go all the way to 10, okay? Without trying a second time, right? So anyway, okay, we'll see you tomorrow, and I'll actually get into more real materials selection, but at least you now